Let's jump right into this. Have you ever looked at a problem and thought, wow, there are just too many possibilities to ever actually calculate an answer? Well, in today's explainer, we're taking on the famous Bug Trap Riddle. We'll be diving into a super cool mathematical concept called recursive probability. It's actually the exact same logic used to build complex computer algorithms. And the best part? We're going to master it by following the journey of one tiny wandering bug.
So, welcome to our puzzle. Picture a tiny protagonist, a little ladybug, just wandering across a magical, chalk-drawn square on a rock. But it's not just a basic square. It has this diagonal path cutting right through the middle, and two mysterious, honestly kind of ominous-looking traps sitting at the top corners. At every intersection, our bug just randomly chooses a path. Equal probability. It's a game of pure chance, and the stakes for our six-legged friend, surprisingly high.
Now, to actually solve this, we need to translate that real-world setup into a clean mathematical model. If we strip away the rock and the leaves, we get this precise diagram. We've got 4 vertices, A, B, C, and D. Our bug kicks off its journey down at vertex D in the bottom left. Vertex C in the bottom right is our other safe zone. But look up top, vertices A and B are those traps. And take special note of that solid diagonal line slicing directly from A to C. That specific piece of geometry is absolutely crucial, and it's going to heavily influence our bug's fate. Okay, let's lay down the ground rules. Our bug's ultimate goal is to safely reach trap A. We're going to call landing in trap A a success. On the flip side, tumbling into trap B, that's a failure. And here's a super important rule to keep in mind. Once the bug reaches either trap, the whole process just stops cold. Game over. The bug doesn't keep wandering, it has no memory of its past moves, making every single decision based solely on where it is right at that exact moment.
Which brings us to the crux of this entire explainer. The riddle we need to answer is this. If the bug starts at vertex D, what is the exact probability that it reaches trap A, our success state, before it wanders into trap B? Think about that for a second. The bug is moving completely at random. I mean, it could take one step and win, or it could bounce around the board for hours before finally hitting a trap.
Your very first instinct might be, hey, let's just list out all the possible paths and calculate the odds. But think about the sheer contrast here. Sure, we have short, simple paths, like moving directly from D to A. But what about the wandering paths? The bug could go D to C, back to D, back to C, back to D, and then A, or, do that 100 times. If we actually try to track every single move, we'll quickly fall down a chaotic rabbit hole of infinite possibilities. We literally cannot solve this by just making a list.
So instead of tracking the past or trying to map out some infinite future, we use a magic trick, recursive probability. It's this incredibly clever mathematical maneuver that basically says, hey, forget the path you took to get here. It only cares about where the bug is standing right now. By summarizing the unknown future based entirely on the current state, we bypass infinity altogether. It's all about anchoring our math in the present moment.
Let's build our foundation by assigning variables to these unknown chances from our safe vertices D and C. Let's say X is the probability of reaching A before B if we started D, and let's call Y the probability of reaching A before B if we started C. Now, what about the traps themselves? Well, if the bug is already sitting at trap A, the probability it reaches A before B is obviously 1. It's a 100% certainty it's already there. But if the bug is at trap B, the chance of reaching A before B is 0. It's already failed. Those known trap values are the anchors for our unknown variables.
We're going to slow down just a bit here, because this perfectly illustrates our first equation. Put yourself in the shoes, or, well, the 6 legs, of the bug standing right at vertex D. You look around and you have exactly 2 paths you can take, straight up to A or over to the right to C. Because the choice is random, they're equally likely, so our probability X is just the average of those 2 outcomes. Going to A means immediate success, an outcome of 1. Going to C throws you into that new unknown state Y. Therefore, X equals 1 plus Y, all divided by 2.
Now, let's teleport our bug over to vertex C. Viewing the board from this corner, the bug suddenly faces 3 choices, not 2. It can move up to B, left back to D, or take that diagonal straight to A. This is what builds our second equation. Moving to B is an immediate failure, so that's a 0. Moving back to D gives us our first unknown probability, X. And taking the diagonal to A, boom, success, that's a 1. Since there are 3 equally likely choices here, the probability Y is simply the average of these 3 distinct outcomes. 0 plus X plus 1, all divided by 3.
Just look at what we've created here. These 2 perspectives rely beautifully on each other.
X is defined using Y, and Y is defined using X. Now you might be thinking, wait a second, isn't that just circular reasoning? We don't actually know either of them. But actually, it's not circular. It's a structural loop, a system of relationships. By defining the unknown probabilities in terms of each other, we've taken a chaotic, seemingly infinite process and transformed it into a neat, finite system of two algebraic equations that we can absolutely solve. Let's gracefully step through the magic of substitution to untangle this recursive knot. Think of it like a secret shortcut. We want to find x, right? We know x equals 1 plus y divided by 2. We also know exactly what y equals from our second equation. So we simply take the definition of y, which is 1 plus x divided by 3, and plug it directly into the y spot in that first equation. Suddenly, we have an equation with only x in it. When we add the 1 to the fraction in the numerator, we get 4 plus x over 3. And dividing that whole thing by 2 gives us a beautiful consolidated equation, x equals 4 plus x, all divided by 6.
By simply rearranging this, the chaotic infinite paths suddenly collapse into a beautifully clean algebraic answer. We take our equation and multiply both sides by 6 to get rid of that pesky fraction. That gives us 6x equals 4 plus x. Next, we subtract x from both sides, leaving us with 5x equals 4. And finally, just divide by 5. Just like that, all the endless possibilities, the back and forth wandering, it all perfectly resolves into a single fraction.
And there we have it, the triumphant resolution to our mathematical riddle. 4/5, or, if you prefer percentages, 80%. If our bug starts at vertex D, it has an 80% chance of reaching the safe haven of trap A before it accidentally stumbles into the doom of trap B. And just for the sake of completion, if we plug that 4/5 back into our y equation, we'd find that starting at C gives the bug a 3/5 or 60% chance of winning.
Bringing this back to reality for a second, let's talk about what this fraction actually represents. It's really vital to understand that 4/5 describes a natural frequency, a long-run tendency. It absolutely does not predict the exact results for a small group. I mean, if you drop 5 bugs on vertex D, you aren't guaranteed that exactly 4 will survive. But if you imagine a massive simulation with 100 bugs starting at D acting totally independently, the laws of probability tell us that about 80 of them will reach A first, and about 20 will meet their end at B. And honestly, if we take a step back and just look at the board, it makes complete logical sense that this chance is much higher than 1/2. The board is fundamentally rigged in the bug's favor. Why? Because from its starting point at D, it has a direct one-step path to victory at A. And even if it moves to C, well, C also has a direct one-step diagonal path to A. Meanwhile, there is literally no direct path to the failure trap B from the starting point D. The geometry of the space completely dictates the probability. Before we wrap up this explainer, I want to leave you with a brand new puzzle to ponder. We just saw how the diagonal from A to C skewed the odds to 4/5. But what if we wiped the chalkboard clean and drew the diagonal the other way, connecting B and D instead? Everything else stays exactly the same. Traps at A and B start at D. Based on what we just learned about direct paths and recursive equations, what's your prediction? Will the bug's chance of reaching A before B go up, go down, or stay exactly the same? I highly encourage you to set up the new x and y equations and solve the system for yourself to find out.